In this session, we are going to introduce Gaussian mixture models. That means we'll assume all the clusters formed based on the Gaussian distribution with different parameters. We will first look at the Gaussian distribution for univariate, that means for single variable, and for multivariate, that means for multiple variables. We first draw some plot and contours for Gaussian distribution. For example, we can see for this plot, this is the Gaussian distribution for univariate for the single variable. The parameter like this one is mu, the mean is 0, sigma, the standard deviation, is 1. This is a typical standard bell curve. Then for mu equals 5 and sigma equals 2, we can draw a curve like this. Then for 2D Gaussian distribution, we give mu and sigma. We draw the contours for the one set of parameters mu and sigma here. For another set of mu and sigma covariance matrix, we'll draw like this. Okay. So this is a typical way to have a visualization of different parameters for Gaussian distribution. Now we study Gaussian mixture model. We assume every cluster C sub I is characterized by a multivariate normal distribution, where f sub I of x is the probability distribution of x attribute to cluster C sub I. That means we can represent this density function of x under the cluster C sub I. Its parameter is mu sub I and sigma sub I. Mu is a mean, and sigma sub I is a covariance matrix for the cluster I. And we can write in the typical Gaussian distribution form for multivariate. Then we can assume the probability density function of x is given by all the k-cluster normals from a Gaussian mixture model. That means we will say the density function f of x essentially is defined by summation of all the k-clusters. So each k-cluster, the density function is f sub I of x. The probability of this cluster is p probability of cluster C sub I. Then we can represent in the parameter form is mu sub I and sigma sub I. We can say for all the k clusters, each cluster, the parameter is under the condition of mu sub I and sigma sub I. Okay. Then the prior probability p of C sub I, if for all the k clusters they added together, their probability should be 1. So we call this is mixture parameters. Then our task is try to get maximum likelihood estimation of the model parameter. Essentially is if we want to say, given the data set D, what's the probability under the model parameter theta, we can generate this whole set of D. Since we assume all these these n points are independent, we can think their probability is their probability density function of x sub j. They all multiply together for all the n points. We get this. If we write this in log form, so we can take the log of this function, and this multiplication by taking log, it becomes summation. So the computation could be more efficient. And these f of x sub j, we can use the previous one to substitute this function here. Then maximum likelihood estimation is to choose the parameters set theta, so to make this probability to be maximized. Or we can say we can thinking to maximize the log likelihood. That means we want to find a set of parameters theta. So the log of this probability generation, the data set D under the parameter theta is maximized. However, to directly maximizing this log likelihood over theta is hard, is very expensive. So we can use EM approach to find the maximum likelihood estimation for the parameter theta. The EM approach essentially consists of two steps iteratively. One is expectation, another is maximization. The expectation is given the current estimate of theta, we try to compute the cluster posterior probability. That means we want to compute what's the probability of the cluster C sub I under the condition of X sub j. And we can use the Bayes theorem to write in the Bayes theorem form. That means we want to find the probability of C sub I under the condition of Xj. It is actually the function, essentially the numerator is actually the density function of X sub j for cluster sub I times the probability of cluster sub I. Then the denominator is all the k clusters for each cluster that generated j. Then we were thinking about the probability to generate a cluster C sub A. Then for all these k clusters, we add all these together. That's our denominator. Okay. So for maximization step, we essentially is using the computed cluster posterior probability to re-estimate the parameters theta. That means we want to re-estimate mu sub I, sigma sub I, and the probability of C sub I for each cluster C sub I.